Okay, looks like we are live. All right, everybody out there in TV land. Oh, I'm putting that stuff, huh? All right, we will go to the notes, and they're still working. That's amazing. And today's topic is a long thing: causality, correlation, randomness, probability. And we're going to discuss cause and effect, correlation, and randomness. Sadly, not in that actual order, because this was assembled by me incorrectly late last night. Probably not the first time you've ever heard that.
It's fine. We'll forgive you this time.
Oh, thank you so much. Damn senators, they get a taste. So what is causality? So the simplest is it's the relationship between cause and effect. So who can think of everyday examples of cause and effect? Well, Elizabeth can, because she went and witnessed what happens when you mixed chirogenic hydrogen, oxygen, and somebody holds a Bic lighter at the right place.
Very big.
Not good. They were telling us stories like NASA. Water is a bitch.
Yeah.
Well, only if you electrolyze it into its
You
components.
upset it enough.
Which kind of water?
Yeah.
There's,
Plain water, bro.
Plain water. Literally
because there's
hydrogen.
like, there's 44 different types of water.
I didn't ask you for water. It's water. Just take it as water, man.
So anyway, cause and effect. So all the water in the ocean is caused by somebody fired a rocket at some point in geologic history? Probably not. In classical physics, things cannot occur before they're caused, and that's up there on the board. And that is why that whole time travel stuff that we're all hoping somebody will figure out probably isn't possible, but just in case.
Yeah.
Actually, they just published a paper that said it's possible.
One direction though. No, going
No.
back in time, not waiting self to come through that door.
They said going back in time is actually possible too. It's just not for larger masses.
Yeah, they're full of crap. Maybe not. Maybe you can. Anyway, so that's one type of causality, but that's not what we're really worried about in this class. We're more worried about using observations of processes and trying to assign causes to them and figure out how to manipulate that to our advantage. So we will skip the physics thing. I do want to point your attention to the two readings here, because they are worth taking a look at. The second one especially. The second one was written by an undergraduate student someplace famous, who I guess was bored in a class like this and took their 15 minutes and wrote a very nice paper on. I think there's probably more to it than that, where they discuss causality in a time loop sense. We're more interested in cause effect in a data science or data description kind of sense. So let me, I'm gonna have to do it. Oh, it's gonna work, cool. So let me point your attention to this picture. And what we're worried about is cause effect in the almost the literary structure, although this is not a writing class. If the statement why is answered by something, because that's cause and effect. So for example, why did you do poorly in this class? Because you didn't show up, but that only applies to the invisible people here, none of your live people here. That's cause and effect. I did poorly in the class because Dr. Cleveland's a jerk. That may possibly be, that may be plausible, but that's probably not the truth. So that's not cause and effect. I did poorly in the class because the Russian Federation invaded the nation of Ukraine with 150,000 troops. That has not a damn thing to do with your performance in this class. Maybe psychologically it might, but it doesn't have much to do. So that's the difference between cause and effect. Now, your performance in class might be correlated to watching too much CNN and scaring yourself, realizing that most of you in this classroom, with the exception of Ray, are of the age where you can be drafted and get to go play. So I'm not either. I'm not worried about that either.
I can still be called up, but my disability precludes me.
But we could just duct tape some explosives to you and walk you in the right direction.
I've done that before.
So anyway, psychologically, it may have had some impact. Let's look at something somewhat related to cause and effect, which is probably of much more substance in data science. So look at the chart that's on the screen behind me. The blue line represents the total number of lawyers in the American Bar Association, which is a group of drinking people that get together and they drink and then become lawyers. And the orange line represents the money spent on pets in the US. So here's an interesting conjecture. Those two lines they're practically on top of one another. So one could logically say, well, geez, if you spend money on pets, it makes lawyers. That's a horrible thing. We need to outlaw all pets because that way we'll get rid of all lawyers and life will be better for the world. Is there a cause? Do pets cause lawyers? I mean, that's ridiculous, and that's by design. They don't cause lawyers. An economic system that allows enough disposable income to be able to pay for lawyers also is going to tend to select for more and more pets. And so the correlation between money spent on pets and lawyers is good, but having pets doesn't cause lawyers. It's general socioeconomic conditions that improve overall wealth that create sufficient disposable income to have pets. And by pets, I mean companion animals, little puppy dogs and stuff, not meals ready to eat that go bark. Also creates conditions for lawyers to proliferate, hence we have a really good correlation. Another video that you can watch in your own time is this YouTube video on correlation and causation, which has similar examples of the difference between cause and correlation. So correlation does not mean cause, although it's a really good predictor of a lot of things. Let's look at a couple of other interesting examples. The concentrations of atrazine and nitrate in shallow groundwaters out on the West Coast are measured in wells, and for each sample, it turns out that as atrazine concentrations increase, so does nitrate. So ignoring the final question in that sentence right there, in that paragraph, why would atrazine and nitrate at all be correlated in groundwater?
Farming.
Yeah, what is atrazine?
Atrazine's a pesticide.
A pesticide. What's nitrate?
It's a fertilizer.
Yeah, and so it would make sense that pesticides and fertilizers would kind of track one another because they're both, if you're going to put pesticides on it, you might as well put fertilizers on it and vice versa. Or if you're the Monsanto Corporation, you sell them a fertilizer with atrazine booster. It's a thirst mutilator. It's got electrolytes.
Not the ones you want, but the ones you need.
Okay, so you get the picture there. So it makes sense that those would be correlated. And if we were to plot concentrations of one versus the other in a scatter plot, there would probably be a strong positive correlation. You can think of it as a cloud of dots that go from the lower left-hand corner towards the upper right-hand corner. Second example, streams in the Sierra Nevada draining the mountains of California usually receive less precipitation in November than other months. And two questions come to mind, which is that conjecture true or not? How would you test that? In words, I mean,
You can always check drought charts.
trout charts.
Drought charts.
Oh, drought charts. Okay, I heard trout charts. I was like, we're fishing. Okay, cool.
The drought charts that they use in California and for the Nevada water supply system for Hoover Dam.
Okay, that's one way. Any other ideas come to mind? Anybody? That's not a bad way, but there are others. So why not get all the precipitation from January for December for California? For how many years? 70? And how would you assess if the rainfall in November is smaller than the other 11 months?
Precipitation for every month for 70 years.
Just do the same way you did on the exam. You all got that problem right with children and mothers and fathers. It's the same problem. Get the mean value for each of the months. And if November is smaller than the other 11, that's a pretty strong indicator that that statement might be true. And if it's a lot smaller, it's even more true. So, okay, you know how to do that. You actually did it on the exam. Most people got it correct. Apparently you forgot as soon as you hit submit, which is not unheard of.
It's American way.
As soon as you logged off your check account, it was gone. The next part of the question is, has the amount of November precipitation itself changed significantly over the last 70 years? How would you assess that statement? You wouldn't. Okay, so I got that. Absolute silence. You wouldn't care. What if there was $1 million involved in it? $1 million in your pocket, tax-free?
You do a comparison of November's
Okay,
precipitation throughout November for 70 years.
70 years. And so if the 1930 precipitation, if indeed the precipitation is showing gradual change, the 1930 would be the same as or different than yesterday's?
Different.
Different. Good. Both those situations, at some point, we would have to assess how strong that correlation is. Is it really obvious or is it kind of meh? And one class of measures we use to do that are called correlation coefficients. It's also important what the level of significance is, but that's for a later day and time. So a couple of association measures. One is called covariance, and it's just a measure of the joint variability between two random variables. Here's the formula for it. You already know how to convert that formula into a Python script. Or if you're smart, you use the statistics package where it's already built in, no brains required. But look at what it's doing. It's taking a series X, subtracting off its mean, and then multiplying that by its corresponding values in a series Y, where their means are subtracted off, and then dividing by some constant, happens to be n-1. So that's all a covariance is. Is there any requirement that X and Y be different series? That'd be a no. If indeed they're the same series, if the covariance of X with itself is evaluated, what's the other name for that? You've already seen it. Someone in the morning class guessed pretty good on that, so I'll give you guys a chance to do even better. So the covariance of X versus X is also called the damn close. That's a damn good guess. It's actually the square of the standard deviation, the variance. So very good. That's about the best the morning crew did. So you haven't even had statistics, and you can do statistics. So once you get in the statistics class, you're going to go ahead and take your perfectly good innate capabilities, and they should have it destroyed by week 3, give or take. It depends on how they clutter it up. If we normalize the covariance, that's called a correlation coefficient. So normalizing means we make it range between -1 and 1 instead of minus. I guess this could get to -infinity and infinity. And here's what the pictures look like. If we have positive correlation, it's like everything's starting from the lower left corner, working its way to the upper right corner. Negative correlation, the opposite's true. And zero correlation is the most upsetting thing to ever discover, because it means there's not much information provided by knowing the value of X when we're trying to predict the value of Y. Let's look in the positive correlation picture for the time being. So we're in this leftmost picture. Anybody who's actually looking at the screen, hold up your thumb. There we go. Okay, so we got thumbs up. So if X is right here at this left edge where the cursor's moving up and down, hopefully making you nauseous. So you remember from West Side Story, nausea. Okay. What's the corresponding value of Y? Is it down here or up here? Yeah, it's down here. And then as we move to the right on the x-axis, maybe somewhere out here, the corresponding value of Y also goes up. We don't know what rate that's occurring, but as X gets bigger, Y gets bigger. That's positive correlation. On the other side, if we start with a negative correlation, as X gets bigger, Y gets smaller. That's negative correlation. We get to the 0 one, as X gets bigger, we have no idea what Y is doing. Best we can probably do in that case is get the mean value of Y, and that's about all we know. Okay, one of the types of correlation coefficient is called Pearson's R, and right here is the formula for computing Pearson's R. This is actually harder to typeset than it would be to script in Python. You can see we have an X squared term and a Y squared term, so it's almost putting the covariance down in the denominator there somewhere. And we have ends and cross term right there. So it's got all the pieces of a covariance. It's just modified in such a way that it returns value between -1 and 1. And here's the same three pictures again. Positive correlation, so-so correlation, negative correlation. Let's just summarize that. A correlation coefficient of 1. So if Pearson's R is equal to 1, that means for every positive increase in one variable, there's a corresponding positive increase in the other variable. Not necessarily 1-to-1, but if one goes up, the other goes up. So for example, if shoe sizes go up, they go up in almost perfect correlation to foot length, since basically that is the definition of shoe size. Correlation coefficient of -1 means that for every positive increase in one variable, there's a corresponding negative increase in fixed proportion of the other. For the example, the amount of fuel in a tank decreases in almost perfect correlation with vehicular speed and time of travel. Unfortunately, you can't go slow enough and still move to get zero fuel consumption. Back in the early days of programming aircraft to fly by themselves without human intervention, the Army was doing this in Huntsville, Alabama. That's where they do all the helicopter stuff. This with the UH-1 helicopter. You see them in movies now. You don't see them in real life much anymore. They're usually stuck on the top of a pillar in front of a VFW building. But anyway, in the early days, they put all this computer crap on them to see if they could fly themselves. And they did, and they flew pretty good. The only thing was the programmers at the time didn't go deep enough into the code. The computer thought that if it flew backwards, it would make fuel because of some bad correlation. I mean, the correlation was correct, but it didn't work. They always wondered why the things would fly backwards until they ran out of fuel. And it's like, then when they went and looked at the control software, it's like, oops, that was only a $250,000 screw up. Well, they were able to fix it. At least they figured out what happened before it crashed. It had to be terrible to be the pilot that was in that was like doing So I mean, this was like self-driving cars, self-flying helicopters. Actually, a self-flying helicopter is way easier than a car because all you have to do once it's in the air, you stay away from the edge of the air. It works fine. Zero means there's no information. The two simply aren't terribly related. So let's consider an example. And we're going to just look at the concept of association. So we're going to go back and get our elapsed time and speed from, we dealt with that before. This is the same table as before. We'll create a data frame. So we'll load in our friend NumPy and his bearish friend pandas. We'll import the statistics package so that we don't have to script in the covariance and the Pearson's R. That's the only reason to do it. Someone else has written the script. We should use their work. They put a lot of time and effort into it. What makes us so arrogant that we think we could do better? Other than it's on the next test. But anyway, we'll import our Python plot. So here we create the data frame. No surprise here, I would dare say that everybody in this room now would be able to do this all by themselves, no help. Even in a test situation, you might be able to be able to do it correctly in an hour. That was not a intended jab. It just came out that way. This converts it into a data frame. We're naming the data frame data. And let's go ahead and have data regurgitated back to us. Ta-da, time and speed. Now let's explore the data. Remember what the describe function does? What's it do? That was a perfect answer after a huge yawn. It tells us how many things are in each series, tells us the mean value of each series, standard deviation, smallest thing, biggest thing, median thing, 25th percentile, 75th percentile. That's what describe does. That's what its purpose in life is. So from that collection of numbers up there, what can you say about the relationship between time and speed? Not a whole lot, except as at the 25th percentile time, the speed's 9.5, and at the 75th percentile of time, the speed is almost 70. So there appears to be an increase in speed corresponding to an increase in the value of time. Let's go ahead and get the variance of the two. So the time variance and the speed variance are here. We'll report the variances. So the variance of time is 11. That's just a computation. If you can't get the variance of time, you can take the standard deviation and square it. And sure enough, 3.31 squared should be 11. I'm not going to test that conjecture. I'm going to assume that the computer did it right. And 41.2 squared is 1697. So let's find the covariance. So we use the covariance function, which is built in. It turns out the covariance of time with itself is 11. Big surprise there, right? It's the same as the variance is supposed to be. And the covariance of speed with itself is 1697. Also, big surprise there. It's supposed to be that. But here's the interesting one. The covariance of time and speed is 131. Now, the magnitude of that doesn't mean much. The fact that it's positive and substantial when compared to the variance of time is indicative that there's some relationship there. It's telling us that if we know something about time, we know something about speed to a factor of about 10. If we use the Pearson's correlation method, we get the following correlation coefficients. Time has a correlation coefficient of 1 with respect to time. Does that make sense? Does it not make sense? The quiet left side. We're going to be here for another hour and 20 minutes, so might as well play. Yes, it makes sense. A variable should be very well correlated with itself. It should always be perfect. Similarly, we get the one fact for speed versus speed, but here we have time is correlated with speed at a value of almost 1. So there's almost a perfect correlation of time and speed. The correlation coefficient doesn't give us information on what that relationship is. It's just that there is a strong positive relationship. So us being very good hackers, we could probably hack a usable linear model as speed u is approximately equal to the average speed multiplied by the covariance of u and t divided by the covariance of time with its spell multiplied by t minus t bar. So there is a hackable, I hacked linear model based simply on the covariance. We'll go ahead and create our plot. We'll build the model, we'll make the plot, and that look familiar? Yeah, how much trial and error was involved there? The other end of that. None, there was no trial and error. Yeah, all we did was get the correlation coefficient, postulate a fairly simple linear model, and we get that result. Remember back when we did it by trial and error, you had to guess values of intercepts and slopes and so forth. So the advantage here is basically we've just done what linear regression does. So if we know there's a correlation, we can use that to our advantages. So some of the implications of that are in, oh, let me get back to this before I go to the implications. So we have a strong correlation. Time apparently gives us a pretty good ability to predict speed. But does time cause speed? We don't really have any evidence of that in the information. Time might be on your side, but it doesn't cause speed. What causes objects to gain speed, Elizabeth?
You apply force to it.
There's, she's right. You apply force on it, and that damn Newton's second law says it's got to go faster and faster and faster. So what's one way of applying force? Again, picking on you, Elizabeth.
Wait, what?
What's a way to apply force to an object? Something you just witnessed.
Punch it.
Punch it. Duct tape a big ass rocket to it,
Yeah.
put fuel into it, and hold a Bic lighter until you get it to spark off. So rockets apply force for how long? So in the whole scheme of things, is that a long time or not very long time?
Not a very long.
Yeah, who applies the impulse longer? A 747 flying from Houston to Bahrain, the long way, or a rocket,
Long way.
or a rocket going from, where is SpaceX? South Texas somewhere up to 100 miles above the Earth. Rocket burns in that case for what, a couple minutes? That 747's got to burn fuel for 14 hours. So in those two cases, the time involved is much different. So time has a role in that the force applied for a particular amount of time is what causes the speed to increase. So hidden in this drawing is the force component. It's hidden in that blue line somewhere, right there, right there. You gotta look close. I'm making that, I'm being a smart ass. Okay, keep that in mind. Most research questions, ultimately, we're trying to explain cause and effect. In experimental research, we often can construct the experiment so that what we think are the causes produces a response, and we would consider the experiment a failure if the presumed causes don't elicit a response. In things like rockets and duct taping rockets to objects and squirting them up into the sky, that's pretty straightforward. Other experiments are a little tougher. So the experiments that people do over in the pharmacy school and in the medical center, they get poisons out from the dumpster and they put them into people and hope it makes people better. And a lot of times it does, but we don't really know if it's the poison that made the people better, if they were just going to get better anyway. So the standard experimental case in that thing's increase the amount of poison. That's medical research and biological research and a lot of other research. I'm making light of it, but that's not the intent. When we design experiments, we have two groups. We have the part of the experiment that's going to be exposed to what we think a cause is, and the part of the experiment that's treated identical, except it's not exposed to that cause. And if there is a cause-effect relationship, we anticipate that at the end of the experiment, the parts of the experiment that have been exposed to the causal agent will have different outcomes than the parts of the experiment that don't. And in experimental research, you can usually pull that off. In data science experiments, which I'm not really sure those three words should go together, but wherever I stole this from, they did. Causality might be impossible to establish. However, we can certainly establish correlations. We've already established a correlation between time and speed, and we can exploit that in many senses. So in data science, a lot of studies involve observations on a group of individuals. And then the cause or the factor of interest is called a treatment, or an explanatory variable, or a predictor variable, or a predictor feature, on and on. There's a lot of names for it. And the outcome is called a response, an effect, a state, a predicted value, and so forth. It's measured on each individual. And then the presumptive establishment of causality takes two stages. First, we observe an association, get a correlation. Second would be to try to establish the strength of that correlation. And one way to do that would be to control all the possible variables other than the explanatory variables. Generally, in real data, that's impossible to achieve. A second approach is to establish randomized control studies. So to randomize, we take a sample from a population, we randomly assign members to either group 1 or group 2, expose the two groups identically, except the control group receives a fake treatment, compare the responses of the two groups. If they're the same, then there is no evidence that the treatment variable caused a response. If they're different, then there's evidence of that. There's no guarantee. And with some ingenuity, we can extend that to engineered systems and natural systems. So let's again just do some more thought experiments on causation. Imagine, if you will, we have a plot of some sort of virus in from the MMWR in Texas, and we look at this chart. What kind of chart is this, by the way? A histogram. It has yellow bars, orange bars, and a few little green ones, and a little blue one right here, and a teensy itsy bitsy red one. And the orange bars are H1N1, which is a type of influenza, and the yellow bars are a type A influenza, not otherwise subtyped. And then there's a few other colors here for fun. And we noticed something interesting about influenza. It's kind of just sort of running along all happy, April, May, June, July. And then at the end of summer, when it's time to go back to school, boom, it just skyrockets here. Now, is that because people get sick so they don't have to go to school? Possibly, but I doubt it. Or is it because all this relatively low level infection now has to go 8 hours a day to the same building and sit together in a room like this and have some blowhard like me blow hard, and it gives a chance for all those bugs to transfer from person to person, or maybe they're just swapping spit or something. And so then it goes up, September peaks. In this case, it peaked in September, starts to make its way down, and lo and behold, oh, it's Christmas time. Boom, it just plummets. That's because everybody wants to go home for Christmas, so they get better, because you don't want to be sick during Christmas. So does going to school cause the flu? I mean, it doesn't make sense that it causes the flu. Is there evidence that going to school causes flu? Not really. Does having the flu cause people to go to school? That too is an absurd statement. There's no way that they're related. Does going to school contribute to the spread of flu? Well, we got pretty decent evidence of that during the school season, we get lots of good flu. You could substitute COVID if you want, or any other bug du jour. Does the spread of flu contribute to school attendance? That's also absurd. It does not, because if anything, people get sick, you're supposed to go home and be sick in the privacy of your own garage. Are there other variables that affect both? I mean, is it odd to you that the peak occurs kind of in the latter part of the year when the weather is changing from warm and comfy and good old beach weather to cold and cramped stay indoor weather? Those are called confounding factors. So the underlying difference between the two groups, if there is one, is called a confounding factor because it might confound you when you try to reach a conclusion. For example, in the previous example, cold weather is probably a contributing or confounding factor that's hard to separate. Going to more engineering kind of things, for example, flood flows are very well correlated to drainage area, main channel length, mean annual precipitation, main channel slope, and elevation. And I have a data set. I can't prove that. I could demonstrate those conjectures to you. I'll just hope that you'll trust me and let me continue talking. However, the main channel length itself is strongly correlated to drainage area. They're practically square roots of one another. So much is to be useless as an explanatory variable if we're keeping drainage area in a data model. So if we're going to use drainage area as a predictive tool for flood flows, we don't want to also use main channel length because they're both essentially predicting the same thing. That would be called a confounding variable in this context. Let me skip ahead since we get to just segue straight into lab. We'll come back to this in a minute. Next part is to teach you how to do casino gambling.
Yes.
Let's see if I can, I want to get to the one. Okay, so let's take a quick foray into randomness and probability. If you want to read about randomness and probability, you can click on this link and it takes you to this book from Berkeley on randomness and probability, or you can just look at my pictures. Okay, so over the centuries, there's been considerable philosophical debate about what probabilities are. Some people think probabilities are relative frequencies, and that's probably probably the predominant thinking. Others think that they're long-term relative frequencies, and others still think that probabilities themselves are subjective measure of their own personal degree of uncertainty. As a practical matter, most probabilities, at least in engineering, are relative frequencies. If you're Bayesian, then it's just a conditioned relative frequency. By convention, probabilities are numbers between 0 and 1, or equivalently 0% or 100%. Impossible events are assigned a probability of 0. Sure things are assigned a probability of 1. So for example, what's that picture jumping out at you right now? It's either a great white shark or a trial attorney. It's hard to tell the two apart, jumping out of the water. So what is the chance of there a great white shark walking through that door right now and biting me in the butt? Yeah, it's probably as close to 0 in probability world as you can get.
Is it possible?
And I actually don't think so. I guess if you put the great white shark in a tank and helicoptered it in here, somebody carved a hole in the ceiling, dropped the shark in the tank, and as it's flopping around all angry, we could get bit. So it's possible. So yes, so technically it's not 0. The chances of that happening though are far less than my chances of winning the lottery without buying a lottery ticket. So it's low. Okay, so here it is in words. Great white shark swimming up your sewer pipe, biting you on the bottom is 0. Unless the sewer pipe is big, the shark physically can't get to you. That is the definition of impossible. If you're swimming in a freshwater river, say the Columbia River, which is somewhere near Oregon, that probably a shark bite probably increases a bit, perhaps 1 in 100 million, although your chance of getting beat up by a protester is far greater. Or 0.0000001% chance of a great white shark, which happens to be a pelagic species, so it doesn't get up into freshwater. Having to swim upriver freshwater, has to go up a couple of fish ladders, or at least 2 dams, and still be hungry enough to bite your bottom. It would be a rare bite indeed, although not physically impossible.
Sharks do it all the time.
He had other sharks. Now let's look at this next picture. There's this old dude here with a hat and a beard, standing on the edge of a rock, and example of a sure thing. If he was to run and jump off that happens to be Glacier Point in Yosemite Valley. That rock right there is no longer there. It's fallen down years ago. And this dude here is no longer around. He's died years ago. Some guy named John Muir, they named a something after him. But if you're to run off and jump off of Glacier Point, it's almost guaranteed that you will have a 1,000-foot plunge until you hit the apron of the cliff. The apron's where the cliff kind of bends back out at the bottom, and you make a big red smear. And if you're going to do that, I suggest you don't. I mean, if life gets that bad that you even consider that, go get some professional help or amateur help. Just get help. But if you're going to do that, at least let your friends know so they can videotape it, because that will go viral. Smear. So that is, yeah, no kidding. So that is the definition of a sure thing. A gust of wind could push you off into the trees and you could land nicely and survive, but that's pretty unlikely. It has happened in the history of people falling off of high objects, but not enough to bet on. So if you don't have a squirrel suit and a parachute, you're pretty much going to expire with probability of 100%. So math is a tool that we use to find probabilities exactly, and the computers are pretty useful for it. And we tend to do it using a technique called simulation. Is we simulate random processes, and then from the simulation, we can make postulations as to probabilities of particular outcomes. And from this, we have to consider the concepts of a sample, a population, and probabilities themselves. And we'll look at some ways of computing probabilities for single events, both events, and an at least event. Okay, so now we're officially into the lab. So I'm going to quickly go through this and we'll go straight to lab. We need these for the lab. The lab makes more sense if we've had the probability discussions. That's why I'm doing it. Okay, so the first way of establishing probability is something called simple exclusion. If it turns out that a particular thing happens with 40% chance, then the chance it doesn't happen is 60%. And that natural calculation is described as follows. The probability that something doesn't happen is 1 minus the probability the thing happens. And the result is correct if in that statement, the entirety of probabilities are enumerated. So the probability of becoming a red smear jumping off a Glacier Point is pretty close to 1. The probability of it not happening is pretty close to 0. You sum those two together, that adds up to 1. You've examined the whole outcome. Second is complete enumeration. Let's suppose you're rolling an ordinary die. The natural assumption is that all 6 faces are equally likely. And the probability of how one roll comes out is easily calculated as a ratio. For example, the chance that the die will show an even number is the number of even faces. So there's a 2, a 4, and a 6. So there's 3 of those. And the total number of faces is 6. So there's 3 chances in 6 that will get an even number. We can play the same game with die chose a multiple of 3. An event happens. And complete enumeration is the outcomes that make the particular event happen divided by the total number of outcomes, the total outcomes. provided that all outcomes are equally likely. We can also modify that for unequal probabilities. In the case of the single die, there's 6 outcomes. These comprise the entire population of outcomes. Notice the word population is bold-faced. So let's go back to our things up here. We're looking at samples, population, and probabilities. So the population of a die, there are 6 faces that can come up. When we roll a die one time, we're taking a sample of that population, and we get one of the 6 faces. It's not that funny, people. And the next thing is, next concept is, so we got all the dies taken care of. If we have 2 die, there's 12 outcomes, 3 die, 18, and so on. So not all random phenomena are as simple as a roll of a single die, but the 2 main rules of probability are applicable to even complex situations. First one is conditioning. Suppose you have a box that has 3 tickets, 1 red, 1 blue, and 1 green. Suppose you draw 2 of those tickets at random without replacement. You shuffle the 3 tickets, draw 1, shuffle the remaining 2, draw another. What's the chance that you'll get the green ticket first, followed by the red one? Well, we have to enumerate all the possible ways of pulling those tickets out. We can get red, blue, blue, red, red, green, green, red, blue, green, or green, blue. All those are equally likely by the sampling scheme, but only one of them gives us the event of green and then red, which is GR over the other 6. So there's 1 chance in 6 of that happening. But there's another way of arriving at the answer, which is by thinking about the event in 2 stages. First, we have to draw the green ticket. That has a chance of 1 in 3. Then we have to draw for the remaining 2, the red ticket, which has a chance of 1 in 2. The product of those 2, 1 in 3 and 1 in 2 is 1 in 6, which gives us the estimate of probability of that particular outcome. The factor 1/2 here is called the conditional chance that a red ticket appears second, given that a green ticket appeared first. We're going to see that in goats and cars in a minute. And then generally we have a multiplication rule in this case. The probability that 2 events happen is the probability that 1 event happens times the probability that the other event happens, given that the first event has happened. Thus, when there's 2 or more conditions, for 1 event to happen as well as another, the chance becomes a fraction of a fraction, which is smaller than either of the 2 component fractions. The more conditions you have to be satisfied, the less likely all are to be satisfied. So in Elizabeth's rocket tour, that thing, when it actually squirts a rocket up into the sky, there's a lot of stuff that can go wrong. Each thing can have a very small probability of going wrong, but as you start cascading all the things that go wrong, you can get a really spectacular event, which is.
Speaking of, did you know Dean Stockwell was supposed to get blown up on the Challenger?
Pardon me?
Our dean, he was supposed to be on the Challenger, and I guess he pulled the long stick.
Yeah, I heard about that.
Mhm.
Well, that's lucky for him. It sucks for the other 6. I think that will get us to the lab. So let me take a 5-minute break while I go ahead and bring the lab up. For those of you out there in TV land, we're taking a 5-minute break. So this would be a good time to get up and get an adult beverage for the afternoon. For those of you that are staying here, we will start Lab 18 in a second. He's quitting. You have no excuse, so I'm going to have to tease you as you leave.
My bus is at like 5:30. It's the last bus. So.
What are you going to do in the future when we don't have this online stuff? Get to your bus, man. No, you don't. There's like 4 views a lab. So if he's 1, who are the other 3? Oh, so I got 4. Oh, I got 6 of you now claiming to do 4 views. Sure you have.
We watched them a couple of times. Actually. So 2 out of the 4. Yeah.
Okay, so let's, if you're gonna follow along, I'll give you a chance to get followed along. Okay, looks like that link is working correctly. So we're gonna look at laboratory 18, causality, simulation, and probability. And let me go ahead and get my, hopefully it's working right now. Got to get some food in me. I'm getting really dizzy now. That was a quick exodus. Everybody had to go to the bathroom. Okay, everybody ready to play Lab 18?
That wasn't 5 minutes. That was 3. No. There's your adult beverage. Like 63%. So it's not essentially Everclear.
That's no, that is not the right.
That is roughly Everclear.
It claims that it's ethyl alcohol,
So it should be the correct.
but I wouldn't test
It's
it.
probably methylated, like 1%, 2%. So you probably might go blind, but is that a risk you're willing to take?
I don't know. I would be very curious of something that's designed in the USA and made in China. We got 2 minutes to go. This will actually be, I don't know why that says 14. Obviously didn't get that changed. 1 minute to go. You have 5 minutes. Adult beverage should be kicking in right about now.
Right around now.
Yeah, I always thought probability and statistics was a lot more understandable in the presence of adult beverages. Unfortunately, here we're not allowed to bring those to class. We're not supposed to. And all those that think you can like sneak vodka in Sprite, I assure you, your professors can smell it.
Sir, where can I find the Lab 18?
Yo.
Because on the Blackboard notes, I go to the
Why don't you just go to the class notes at the end of the class notes?
yes,
Yeah.
the 18 doesn't work. Like,
It works just
on the
fine.
class notes on the computer, it doesn't show anything there.
You got to click on it.
Yes, but can I bring my
I just
computer
did it.
to show you? Yeah, but I get a different thing that I don't like.
But not the metal one.
This is college students figure out how to make drops with vodka. Make mouthwash.
I can smell the vodka, so you need to come up with something better.
Not if you, not if you are.
I go to the lab notes and the 18 lab. Okay, you go to the notes. Oh, I get to click there.
Yeah, it doesn't automatically update.
Oh, okay, that's fine. Why?
You got
Okay,
it.
come
from
back. All right, thank you.
there. Okay, so it's now 5 o'clock, so we can start Lab 18. We got them up to speed on their labs. You got it, Nestor? You got it? Bueno, okay. Okay, so let's look at laboratory 18. We're just going to kind of do this as a workshop. So what is the first thing that you're going to do in your lab? Yep, I'm going to put yo me llamo es Teodoro, como se llama? My R number. What's the next thing to do? Somebody's logged in. Welcome. Oh, wait, let me make sure I have the, what's in call? I just realized.
You're recording.
No, it's not the recording. I want to make sure I don't have a waiting room that's holding everybody out. Nope, it looks like it's working for y'all. So Mark, Jarrett, can you hear me?
Yes, sir.
Okay, cool. So today we just did class and I'm doing the lab because Josh has an animal at the animal doctor. Okay, so it looks like, oh, and there was a chat. Let's see what's in the chat. Got a big yes. Okay, excellent. All right, so after putting your name into the lab, what happens next? Let's profile our computer. So yours will not produce the same output as mine. If you're getting Atomic Kitty and Sensei and your Python 3 is in root, opt, Jupyter Hub, bin, Python 3, you're either logged into my machine, which is possible, or you have failed to profile your computer. All right, so we profiled our computer. So let's look at Python for simulation. So as I was saying in the lecture period, we use simulation as a way to approximate probabilities for certain things. So nice thing about doing it on a computer is we can play Russian roulette without any concern about the consequences for it in real world. Everyone knows what Russian is. So this was always in the notes. The current affairs in the world today, that's entirely coincidental. But so everyone's heard of Russian roulette, right? You take a semi-automatic handgun, you put one round in the magazine and you chamber it, and then you have a 1 in 6 chance. Wait, you have a 1 in 1 chance of it going off. It's played with a revolver. And normally you put one cartridge in, you spin it, close it, and then you pass it around until you get to the end of the scene in Deer Hunter. Although, wait, hang on, let me just mute myself. Okay, so so you all know the game. By the way, it's a stupid game. Don't play it ever unless it's on a computer, where the consequences of failure are.
I mean, I'm not like 99 years old. I don't care.
Yeah, exactly. If
You've
you're
never been shot, have you?
I hope not.
I've been shot 6 times, let me tell you. Doesn't feel good.
6.
Bro, what?
Yo.
I went to 2 wars, what do you expect?
You got 3 more lives?
No,
Cat lives?
no,
Yeah, it's
I've
probably
died,
not live.
I've died 3 times.
Running on overtime.
So
Sudden death.
it
It sucks.
don't mock them. Getting shot hurts.
It sucks.
So we're going to simulate a game of Russian roulette in the computer, and we're actually going to get to use all sorts of cool things like our friend NumPy. And what we're going to do is we're going to create an array, a NumPy array. It's going to contain 6 items. It's going to contain a 1, and then a 0, a 0, a 0, a 0, and a 0. So the 1 corresponds to the cylinder that has a cartridge in it, and the zeros correspond to the empty cartridges. And we're going to name it Revolver. Why? Because that was a good Beatles album, and in homage to the Beatles, we're going to name it Revolver. And we're going to use the random choice function that's built into NumPy. So what random choice does in NumPy is it will go into the array and it will randomly select an item from it. So we're going to randomly select 2 items from the array. So what are the chances? So it's showing a 0, 0 right now. What are the chances of us getting 2 zeros in a revolver that has 1 filled cartridge and 5 empty? 2 empty chambers. What are the chances of that? I just want you to, I don't actually care what the number is. There's a pretty good chance of getting 2 empty cylinders and a pretty low chance of getting 1 full cylinder. Yeah, so let's see what happens. Let's go ahead and run a random choice. And we got 2 zeros. Let's go ahead and do it a few more times. So you know what the print command does. It's just pulling from that revolver. Oh,
You're dead.
bang, we're dead. Let's do it again. So who was the actor in Deer Hunter? Not Robert De Niro, who kept getting the 0-0, but the other dude. That's what happened to him in that scene. Let's go ahead and take 5 samples from our revolver. So the chances of getting a 1 in 5 samples is pretty high. And if it's a real revolver and you're pointing it to your real head, your chances are like, that's as close to a sure thing as you can get, because that's a dumb game to play. Oh, it looks like it's getting reloaded. That's weird.
Welcome to my life.
And if we pull the trigger 10 times, pretty good chance of splattering our brains out. I actually am wondering why the random choice isn't working the way I expect it to. But you get the idea now. So just a little humorous side note here. If you are playing a game of Russian roulette, by all means, choose to go first and do exactly what this person did to his competitor. Take the money and run. So now let's play a different game. We're gonna take a regular dice, goes by the name of D6, so die with 6 outcomes. And we're gonna roll it 10 times. So we roll the dice once, we might get a 1, 2, 3, 4, 5, or 6. Roll it again, we can get a 1, 2, 3, 4, 5, or 6. Roll it again, get a 1, 2, 3, 4, 5, or 6. So again, using the same computational structure, we create an array. The array has the 6 outcomes we want to have happen. In this case, it's the numbers 1 through 6. We assign it to an object called dice. It should be called die, because dice is a plural. Die is the singular. And we'll use the random choice feature in NumPy to roll that die 10 times. And so on the first roll, we pulled up a 3, then a 4, then a 1, then a 4, then a 3, then a 3, then a 1, then a 4, then a 4, then a 6. Interesting, no 2s. That is really bizarre. Okay, at least there's 2s in there. So now let's use that to play a gambling game, which is what Elizabeth was. She got all excited and said, we're going to do online gambling. Okay, so we're going to have the following rules of the game. We roll the die. If it turns up a 1 or a 2, we lose $1. If we turn up a 3 or a 4, it's a push. If we turn up a 5 or a 6, we get $1. So let's go ahead and create our game. So we're going to do it in a function. Remember, in a function, it has the keyword def. We'll call it the D6 game, and the input's going to be the number of rolls. So number of times we're going to play. We're going to have a dice, 1 through 6. We're going to have rolls, which are going to represent the random choice on the dice, the number of rolls that we input, and we'll keep a list of our gains. And then what kind of structure is this thing right here that I have highlighted? And how many times is it going to traverse? The number of rolls. If we get a roll less than or equal to 2, we take our gain list and we append a value of -1 to it. If we get a value less than 4, we append it with 0. This is a tricky if structure because the order of the if is very important. So if we get less than 2, it's going to go to this and exit the if structure. If we get less than 4, we presumably have passed the less than 2 case. So that gives us a 3 and 4. And lastly, if it's less than 6, we have the 5 and 6. And we will return the sum of our gain list. So it will give us the amount of money that we have. So let's just play the game once. So we have a 1 in 3 chance of losing, 1 in 3 chance of going nowhere, and a 1 in 3 chance of winning. Elizabeth, you love to gamble, so what's going to happen? We can win, lose, or draw.
Yeah.
Win. I'm a winner always. Of course. Damn it.
You weren't that time, but that's my fault. Let's try that again. She's a winner.
So,
How about if we play it twice, Elizabeth? Do you think you're going to still win?
I feel lucky, man. I feel lucky.
That's usually when it starts.
And there is,
Usually when it starts.
let's do it 50 times because she's feeling lucky. Oh, man.
Oh, would you look at that?
You play the game 50 times, you netted $11. That's actually pretty
Pretty good,
good.
pretty solid.
Okay, now she's going to play it 500 times. I think her
I'm
chance,
getting better. I'm alive right now, aren't
I think her chances of coming out ahead are
She got one.
slim. Let's see if we can pull up a 0, because whenever this was last done, 500 games produced winnings of 0. But think of what it should produce. It's
Plus 5, minus 5, no more, no less. That's all right.
okay. So we have a +5, -5. How about the quiet side of the room?
House wins.
House wins.
House wins. What'd I say?
500 plays and you walked away with $1. But considering how
You
long,
lost a lot.
considering
You
how,
lost a lot of time, really. You didn't gain it all.
considering how long it would take to play at 500.
House still won, right?
Yeah.
You only walked away with $1.
Well, we
Yeah,
actually,
it's always-
if we did it correctly, we would have to introduce a wallet and we have to put money in it and then you
That's
play,
actually pretty,
you play until the wallet's empty. Let's play another game. So when I was a kid, there was this game on TV called Let's Make a Deal. This dude's name is Monty Hall and his assistant was,
Looks like bad carpet.
so is this before your time, dude?
Yeah,
Just a little bit.
it's
And
like decades before me.
so in the game show, it was kind of like Deal No Deal, but it was better. It was also a lot older and more ancient. But at the end, there's the grand showcase kind of thing. And what you're doing is you get to compete and you get to choose a door. Door number 1. Come on, come on. Door number 1, door number 2, or door number 3. That was Carol Merrill standing by door number 1. And then you pick a door and it's opened. And they tell you what the prize is behind it. You get to see the prize. And then you're given a chance to either keep that door or go ahead and choose
What's in the box?
choose another door. Let's see what the best strategy is for that. I mean, I can do the spoiler alert. The best strategy is to change your guess. And we can demonstrate that using our computer program. Only we're going to do this a little bit more interesting. You either get a goat or a car. Most people want a car. A lot of people don't know what to do with a goat.
Nowadays with these gas prices, I'll take the goat, bro.
Yeah, the goat,
Especially free cheese,
the
free fry. Come on.
trick for the goat is
It's
to
not free to eat grass.
And milk. Oh my god.
It's free lawn care.
you lease it out to people that need their lawn care. Okay, so here's our game.
Have you seen goats? They'll eat anything.
They will eat anything.
They don't die. They will eat anything.
I've seen one
If
bite
it
the
does die, free food.
I've seen one bite the tire.
So a meal ready to eat on the hoof.
Yeah, there you go.
So here's the game. We have 3 doors.
One more and an MRE.
We have three.
Exactly.
We have 3 doors. We're going to be offered to choose door number 1, door number 2, door number 3. Behind the door we choose is either a goat or a car. Obviously, if we pull the car on the first thing, we're going to walk away. No, you have to play. This is
No, I'm saying, is there an option where it's a go, a car, or nothing? Or is it just go to car?
go to car.
It's two goats in one.
Yeah,
car.
there is no nothing object. This is not global thermonuclear warfare. This is goats and cars. Slightly different. Okay, so what we're gonna do, let's go ahead and just play this game in the computer 1,000 times to see if we can infer a good strategy for decision-making. Here's the trick. In the real game, you only get to play it once. So the strategy is use whatever makes you feel you're gonna win. Okay, so we're gonna use a bar plot and we're just gonna discuss whether players are better off sticking to their initial choice or switching doors. So we need to build a bit of a game. So first we're gonna create a function called the other goat. And the input to the function is either goat1 or goat2. If the input is goat1, we're gonna return goat2. If the input's goat2, we'll return goat1. You'll see how this all works out in a second. Next, we're gonna have an array called doors. And there's gonna be a doors as car, goat1 or goat2. Secondly, we'll have an array called goats, which is goat1 and goat2. Now, let's look at the doors array briefly. If we randomly sample from the doors array, we do a random sample of 1, what is our NumPy choice tool going to return from that? It's either going to give us a car, goat1 or goat2, one of the 3. We do it 1,000 times, they'll do it over and over and over again. And now we'll define our actual game, the Monty Hall game. So the user guess is, we're going to let the computer do all the guessing because we're too damn lazy to do this ourselves 1,000 times. It's going to randomly choose a value from doors. If the result is goat1, we're going to return the guess goat2 or car. If the result is goat2, we'll return the guess goat1 and car. If the result is car, we'll return the value revealed and print the information. Finally, we return user guess, the revealed, and the other goat. So let me go ahead and remember to prototype the function. See, I need to prototype other goat, doors. So first, let's check and see if the game is doing what it's supposed to. So we'll play it once. We're gonna let the computer play it once. Sure enough, car, goat2, goat1 appears to be working right. Now we'll create an empty list to keep track of all of our initial guesses, all the times that we had the car revealed, all the times that the car remains hidden, and we'll play the game 1,000 times. And so there is our game played 1,000 times. So our first guess was goat2. The car was remaining. Our second guess, our second time we played it, we got a car. Third time we got a goat, fourth and so forth. Now let's get the count of each item in the first and third column. And now we'll plot a grouped bar plot. Remember how to do bar plots? So if our original guess produced our original guess produces a car 1/3 of the time, a goat 1/3 of the time, and the other goat 1/3 of the time. If we change our guess, we always increase the chance of getting the car. And so as a strategy, it's best to change the guess because the initial chance for being correct is only 1/3. But after that 1/3 has occurred, our change increases that by 50%. We can also use Python for other games. Rolling a dice. In Russian roulette, we had the chance of surviving each round as 5 and 6. And we actually can look at the probability of survival in multiple playing a Russian roulette. I'm not actually going to run it. You can do that on your own. And we see that the number of times we pull the trigger our probability of surviving goes down considerably. And that makes sense. Especially if this is showing that we can pull it 6 times. It's assuming that we're spinning the cylinder every time. Has to be. Because if you had 10 rounds and you didn't do that, you would eventually hit the magic one. So now let's look through an example. What's the probability of throwing an even number on a D20 die? How would you go about figuring that out?
50%.
We could simulate it, keeping track of rolls and probabilities. And then for I in range 1 to 16, looks like this is going to be 15 rolls. We just compute the rolls, compute the probabilities, and then report back what we get. So if we do 1 roll, the probability of getting even number is 50%. If we do 15 rolls, the probability of getting an even number is 0.00031%. And that's because we would have to get an even number, and then again, and then again, and then again, and then again. The more times we take chances, the less chances we have of getting the desired output. We can, sure enough, do that by simulation. We can do a scatter plot, and we see that the probability of even number in sequence after about 4 or 5 rolls is pretty low. So if you're going to play this game, you want to bet somebody, I bet I can get 4 even numbers on this die. That's probably an okay bet. You want to get a good payout for that. But you don't want to bet them, I can get even numbers in 15 rolls. They're going to laugh at you and say, yeah, I'll take that bet, start rolling. And chances are you will lose all your money. How about another example? The probability of throwing at least 1 6 with a D6 in 2 rolls, 5 rolls, 10 rolls, and 50 rolls. So the probability of getting a 6 in 1 roll is 1 in 6. Probability of getting a 6 in 2 rolls, first roll is a 6, which is 1 in 6, or the second roll is a 6, which is 1 in 6. So it actually goes up because it's at least a 6 in one of the rolls. If we do that a lot of times, so let's go up to 50. So we'll do 51. We'll let the simulation run. If we roll that dice 50 times, the chances in those 50 rolls of it getting at least 1 6 is practically 1. You're almost guaranteed that one of those 50 rolls is going to turn up a 6. So how could you use that in an engineering context? What could you use that for? You've just been hired as the lead engineer at the Bellagio. And in addition to your duties of making sure that the mojitos and the other bar drinks are properly prepared and taste suitable for customers, is to make sure that the die are working correctly. So one way to do it is to roll a die 50 times. And if it doesn't produce at least 1 6 in those 50 times, there's something wrong with that die. And you need to go back to the network controller and say, you need to adjust die number 3672 so that it's more matching its behavior. So that kind of makes sense. So that's what simulation is all about. Just go ahead and create a game and then test it. And it looks like this has a bunch of different results. The last one's the one I wanted to get to. So the number of rolls is on the left-right axis. The probability of rolling at least 1 6 is on the up-down axis. And you can see that after about 25, you're almost assured that you should turn up a 6. All right, let's go to cards because Elizabeth likes those too, right? You're a good sport for today's lab. Thank you.
Seriously,
What's
not here in the States.
There you go. That's your answer right there.
you can play cards in Texas?
You can't gamble money on it.
That's why all the casinos are on. Yeah.
Every time you get
There
in
you go to Choctaw. There you go.
every time you get in a car in the state of Texas and drive, you are gambling. You are gambling with your
Gamble on
life.
It's a gamble on your life.
What is the probability of drawing an ace at least once from a deck of cards with replacement? So how many cards are there in a deck of cards? 52,
One piece of spades.
unless it's full of jokers.
Yeah.
So, and we're playing a game with replacement. So what does drawing with replacement mean?
You draw, you look at it, you put it back.
You take the card, you look at it, you put it back
Total number stays
in every draw.
50. Yeah.
Okay, so that's correct. So how do we simulate that? What do we have to do to turn that into a game so we can get the computer to play it? Because carrying cards around is kind of, you always have your phone with you. So might as well just go ahead and play your games on the phone, right? So we have probabilities and we have how many times we're going to draw things. We can simulate each draw. We'll just call that n draws because we have no creativity in naming. And the probabilities of drawing an ace at least once is going to be
4 out of 52. Yeah, 4 aces.
or 1 minus the probability of not drawing any aces, which is 1 minus 48 and 52. And the reason we're doing that way is we're going to be actually exponentiating it to handle the combined probabilities of multiple draws, because we have to multiply stuff together. It's often easier to work on the complement. So draws append I is going to keep track of the draws, and the probability is kept that way. And then when we're done, we'll create a data frame of draws and the probability of an ace at least once, and then we'll go ahead and report the data frame. So let's just do it once. So we should have a 1 in 52 chance of pulling up, we should have a 4 in 52 chance of pulling up an ace. Who can do that in their head? 4 divided by 50 is 1 over 13, right? Which I hope is 0.07. How do we find out what 1 over 13 is? We use this like a calculator. 0.07. Dang, we are good. I don't know what you need me for other than to make this crap up. Okay, so we have a 0.07% chance of getting it in the first draw. Let's do, how many draws do you want to do, Elizabeth?
2.
2. Okay. So in 2 draws, the chance of pulling 1 ace is up to 14%. But now we're going to put some money on it. If you pull up an ace, you get $10. If you don't pull up an ace, you lose 12. So how many times do you want to draw? Yeah, she's into the sure things. That's that SpaceX stuff for you. And sure enough, the chances of her getting the $10 are pretty high. Now let's make it into a casino game. You got to pay for every draw. That's how the house wins. They can give really good odds as long as you're paying for each try.
The people that are at the table, it's like, $150, so I must get you down to 5. All that matters is
Look at a lot of people get a lot of entertainment out of that. As long as they have a bus ticket to get back home, I'm fine with it. Because I get to troll the pawn shops at the end of the week. The remaining examples are for different number of draws. We actually have done that. And again, we can produce a plot of the number of draws, the probability of drawing an ace at least once, and we've already established that at 100, we get pretty close to 1. Any questions? So that was an easy lab, except I going through it quickly. Our next one is an example. Write a function to find the probability of an event in percentage form given outcomes in sample space. This introduces a new part of probability. So the name of our function is prob, and if you provide an outcome and then the total number of things that it can sample from, the probability is the value of outcome divided by sample space, in this case times 100 to get it to a percent, and then we return the value of probability 1. So for example, let's suppose our outcome is 1 and we have 6 different possible outcomes. So the probability of that one outcome is 16.7. What happens if there's 100 outcomes? What's the probability of any one outcome? 1 in 100. And in percent, it's 1%. So we should get a 1 back. Sure enough, we get a 1 back. What if we get 11 out of 100? We should get an 11 back. Yes, the outcome is not the individual thing, it's the total number of the whole. So if we get 11 successes in 100 tries, we have 11% success. So if it's like you guys on a multiple choice test where none of the answers make any sense, so you have to guess B. Let's suppose B is indeed the correct answer, 25 out of the 100 choices. What's your probability of getting the whole thing right? It's just 25. All right, so that's how that function works. Let me put it back. What was I think it was 1 in 6. So that can be used to help establish various probabilities. So let's look at how many king of hearts are there in a deck of cards, Elizabeth? 1. So there's 1 king of hearts. How many cards are there in a deck of cards? 52. So the chances of getting a king of hearts in a single draw is 1 in 52, which is 1.9%, give or take. How many aces in a deck of cards?
4.
What's the chance of drawing an ace? Let me finish the question, damn it. What's the chance of drawing an ace after 1 card has already been drawn?
Out of the deck.
Yeah, how many are left?
If they never have 4 51.
4 out of 51 it is, which is 7.8%. Let's suppose we already pulled an ace. So how many aces are left? How many cards are left? So the chances of pulling another ace are 3 out of 51, or 5.9%. How many hearts are there? 13. Sample space is 52. This looks like a hearts space. How many clubs are there? 13. Yeah, puppy dog feet. The probability of hearts or clubs is equal to the probability of hearts given the sample space plus the probability of clubs given the sample space. So the probability of drawing a heart or a club is going to be 13 and 52 plus 13 and 52. I think should be 13 and 51, but we won't worry about that for the time being. So probability of getting a heart or a club is 50%. Does that make sense? Yeah, that's half the deck right there. Unless you're playing without a full deck. It took me 20 minutes to work that pun up. So, and then again, you can play this game. You can make these things over and over again. So doing simulation in a computer is pretty simple. So let's say you're playing video poker, which is my wife's favorite game in the history of the world. And like you, Elizabeth, she's lucky, which is good because that helps finance her drinking and her playing, and oftentimes the trip to Las Vegas.
He's happy.
You bet. That way I don't have to be entertaining. So what's the chances of getting royal flush in video poker? It's small, okay? And if you know video poker, are you old enough to go to Vegas yet and gamble?
No,
Oh, well, when you do,
I'll take it.
cool. The way the house wins is, even though these are really low chances, the payoff is pretty big, but it's not quite big enough to cover their expected losses. So that's how they always come up ahead. So the chance of getting a royal flush is in the first draw, we have to get a ace, king, queen, jack, or 10. In the second draw, we have to get a king, queen, jack, or 10 of the same suit. In the third draw, a queen, jack, or 10 in the same suit, and so on. And so in that first draw, we're going to take, there's going to be 5 out of 52, then 4 out of 51, then 3 out of 50, then 2 out of 49, then 1 out of 48. And that's assuming that we get the right cards. So when we do that, the probability of pulling a royal flush is 1.5 times 10 to the minus 6, or 1 in 1.5 million. Pretty low odds. Your chances of driving home tonight with a blindfold on and getting somewhere alive are greater. A few more examples with dice. I will skip through those. And my favorite is a bucket with balls in it. It's using the word earn, but nobody knows what an earn is. Who knows what an earn is? Yeah, earn is what you do to get a paycheck. You earn your money. Or it's what you put the ashes in of your various ancestors. I'm hoping you won't need that.
She's
Very
really
s-
betting like her.
That's okay. Get your frustrations out. Go for it. I don't mind. I'll be in an urn someday. Hopefully not too soon. I won't care. So it doesn't. The thing that'll make me mad is if you put me in the furnace before I'm dead. I'm going to be furious. I'm not going to be able to do anything about it, but I'm going to be furious. It'd be just like in that. Was Kill Bill? Was it 1 or 2? I think it was. Anyway, Hollywood has a lot of fun with that. So we have this bucket. It's got 10 white balls in it, 20 red balls, and 30 green balls. We're going to pull five balls out of it with replacement. Let's use simulation. We'll do 1,000 tries, and let's find the probability that we'll get 3 white and 2 red balls in no particular order. The order of white or red doesn't matter, but we pull from this, we get 3 white and 2 red balls, and then we'll play the same game again, 5 balls of the same color. So this problem is stolen from the mighty internet. There it is. And we'll go ahead and work through it. So again, we use all of our tools. We'll get our NumPy. We're going to need a random number generator. We'll create a dictionary to keep numbers and colors stored. So in the dictionary, we have our 10 white, our 20 red, and our 30 green balls. Do you all understand how that dictionary is being built in that script right there? Because that's something that you may not have seen before. So what we're doing is we're establishing keys, which are the colors, white, red, and green, and associating with them with values, which are the I in the counter. It's an unusual way to build a dictionary, but it is just a dictionary. And then we'll do 10,000 trials. We'll set our initial outcome to 0. And then in our simulation, we will make a draw. We'll pull 5 numbers from our bucket. We'll store that in the draw array, and then we'll find out if there's enough whites, enough reds, enough greens. If we get 3 whites and 2 reds, we increment our outcome to outcome plus 1. If not, we just keep going. So does that make sense? We're going to do the simulations. We're just going to draw balls and we'll keep track of red, white, and green. If in a particular draw, we get the value of 3 whites and 2 reds, we increment our outcome counter. When we get done, we're going to take outcome and we're going to divide it by what? It's up there in the code, but we're going to divide it by how many simulations we did. That gives us an estimate of the probability of our desired outcome. This claims the probability of getting 3 white balls and 2 red balls is 0.54%. And it just gone down. Oh, why did it go down? That randomness, man. What do you expect to happen if we do 100,000 simulations? Let me go the other direction. Let's actually have some fun with 10 simulations. So we're going to try this 10 times. What are the chances of getting 3 white, 2 red balls in 10 drawings? Not too good. How about 100 tries? Still not too good. How about 1,000 tries? And now we're getting non-zero results. How about 100,000 tries? Hopefully that's on my home computer. It's thinking now. See right down here where it says the squirrels are running around trying to figure out what numbers to put onto the screen. I may regret choosing 100,000. It's just a little Raspberry Pi computer duct taped to a television set. What do you expect? It's not like it could fly a helicopter, but actually it could. Or control a robot, but actually it could. Or navigate a rocket, possibly to the moon, but actually it could. There we go. So 100,000 was 0.51%. What do we get when we did 10,000? Remember that? It was 0.53. If we keep going up in numbers, it's going to asymptotically approach some fixed value, which is the representation of the true probability. Now the next game is 5 balls of the same color. We just modify the game a little bit. This part of the game is unchanged. And now we have the 2 different outcomes. I'm not going to do too many simulations. And in this case, 3 white, 2 red, we get 0.47% of the time. 5 balls of the same color is a little bit more 3% of the time. So any questions? At the end of the lab is an exercise 1, risk of probability, a little bit of internet research. Be sure to fill that out when you turn yours in. Otherwise you get like half a point off. It's basically how we make sure you do that. Most everything here is an example. So that's all you have to do is that last thing. Let's take a quick look at the homework. So the homework, profile your computer. And next, remember in an earlier lab, you accessed a bunch of concrete data. Then you changed some column names. Then you showed the database, then you made that plot. So you got all the way up to here in an earlier lab. Anyone who actually did it, remember that? Okay. So now what you're asked to do, so it's a cool plot, but the meaningful data science question is, which variables have predictive value for estimating concrete strength? So how do you tell if a set of variables have predictive value? What was the first part of the lecture today?
It was about conclusions and.
It did begin with the letter C.
Yeah.
Covariance, correlation. Okay, cool, good. Now you have all you need to know to do this. Determine the correlation coefficient for the variable pairs. So the key pair is concrete strength is the thing you're trying to predict. And then your predictors are the amount of cement, the amount of blast furnace slag, fly ash, water, superplasticizer, aggregate, fine aggregate, and age. And by looking, you can tell a lot of these don't appear to have much correlation. That's what you'll discover. So you go ahead and code in the correlation coefficient. How would you do that? You have two choices. You could write your own script, or you can go back and look at the lesson and find the actual NumPy command to do it. I suggest you do that second one because your life will be way easier. Do any plotting that you want, build a data model, and we're asked to find, let's see, the cement variable. So here's the model that you want to evaluate. Assess the model. You've done that already. Sum of squares residual. And then play the same game again with age and water. Make the pictures. Answer the last question. What do you think is a better model? Save it as PDF, upload it to the Mighty server, and you're done. You got a week. Any questions? Okay, very cool. That was a fun lab. You all have a great evening. Bye-bye, everybody. Jarrett, you stuck it out for the whole time.